Hello, my name is Chad Quilling. In Speaker for the Dead, sequel to Orson Scott Card's Ender's Game, main character, Ender Wiggin, travels through space at speeds near the speed of light. This allows him to travel long distances in relatively short amounts of time, at least for him. As a result of his space travel, Ender's brother, Peter, ages at a different pace than Ender, eventually leading to his brother, now an old man, asking a still younger Ender to write for him. This seems to be science fiction, but actually it isn't. What Card does is actually an example of a real phenomena called time dilation. What is time dilation? Well, it's exactly what it sounds like. It's time appearing to go longer for one person than another person. So, if time dilation is an actual thing, why do we not see it happening everywhere? I mean, if I get on an airplane, then when I look at my watch, it's not going to be different than the time that I see on the wall in the airport, right? Oh, wait a minute. Okay, we're going to ignore time zones, and then it seems like that we aren't seeing time dilation happening. So why is that? Well, quite simply, time dilation only occurs when the velocity difference between two objects is close to the speed of light. And we can actually calculate how time is dilated using this equation. T equals gamma T naught. So what do these variables mean? T naught is proper time. Proper time is the time observed by a person moving at the same velocity as the object being observed. T is the dilated time, where the time for an object moving at a different velocity than the object being observed. An example of this is proper time would be Ender traveling in a spaceship, and dilated time would be the time elapsed for his brother. That gamma is something that we call a Lorentz factor. It is a factor that is used in many relative physics equations, which time dilation is appropriate for. C is the speed of light, and V is the velocity of the object moving, usually relative to the speed of light. We'll see these make a little bit more sense if we do an example. So let's do that. So here we are, some practice. We have an object moving at 90% the speed of light for 5 seconds. How much time would elapse for a person sitting at rest? I'll give you a minute to try to work it out on your own, and then I will go through how to answer this question. Okay, so let's go over this problem. So if we look at this question, we can see that the velocity of the object that's moving is 90% of the speed of light, or 0.9 c, and we can see that the proper time for this object is 5 seconds. And we also know that the two equations that we're going to need are the equation for the Lorentz factor and the equation for time dilation. So first, we need to solve for the Lorentz factor. We do that by plugging in our velocity into the Lorentz factor, and this gives us a Lorentz factor of 2.29416. We can then plug this Lorentz factor along with proper time into our time dilation equation, this right here. We then multiply the Lorentz factor by the proper time to get the dilated time. And doing this, we get an answer of 11.47 seconds. So that's an example of how time dilation works. As we can see, the object moving at 90% of the speed of light for 5 seconds appeared to be moving for 11.47 seconds to a person that was at rest. Let's look at a different example of special relativity in work. It's called length contraction. Length contraction is exactly what it sounds like. A length seems to be getting shorter for a person, like this. Just like with time dilation, length contraction only deals with speeds that are close to the speed of light. So let's see how we can figure out how much length is contracted. We can use this equation, L equals L naught over gamma, where L naught is the proper length and L is the contracted length. As it says here, proper length is the length of an object measured in a resting reference frame, and contracted length is the length of an object measured in a moving reference frame. Let's look at an example to see how proper time and contracted time are different. So here we have two stars, and we have a person, Mr. Smiley Face, looking at these two stars. He sees that the distance between these two stars is, let's say, 1 light year away. Now, because Mr. Smiley is at rest relative to these stars, that 1 light year away is the proper length. However, if Mr. Smiley started traveling from one star to another at a speed that was close to the speed of light, we can notice something. It appears that the distance between the stars is actually smaller, or contracted. So how can we see how much length can be contracted based on the speed of a reference frame? Let's look at an equation and then look at an example. So here we have that equation again. Again, we already have talked about what proper length and contracted length are. And then we also have our Lorentz factor, which is 1 over the square root of 1 minus v squared over c squared. Again, c is the speed of light, and v is the velocity of the contracted reference frame. So let's look at an example. So here we have two stars that are 30 light years apart. A physicist is in a spaceship traveling 75% of the speed of light, and he measures the distance between these two stars. How long does this distance appear to a physicist in the spaceship? So here's some of the information. I'll give you a second to pause the video, and then we'll go over how to solve this problem. Okay, hopefully you have solved the problem by now. So as we see, the proper length is 30 light years, and the velocity of the physicist in the spaceship, which is v, is 0.75 c, or 0.75 times the speed of light. What is the contracted length? Well, as before, we first need to determine the Lorentz factor, which we can do by just plugging in v into our equation for gamma. When we do this, we then get a number of 1.5119. We then simply plug this into the length contraction formula, 30 light years over gamma, 1.5119, and we get an answer. This physicist sees the distance between these two stars as 19.8 light years. So that is how length contraction can be calculated. Now remember, length contraction and time dilation only pertain when we're dealing with speeds that are close to the speed of light. And so we probably won't be seeing them on a normal basis. However, for any sci-fi books or movies, it's pretty important, or just impress someone that you'd like. Thank you for watching this video, and please like and subscribe to whatever channel this is on. Thank you.